Welcome to the debate. We are at a really critical juncture in electronic design automation, forced there by what experts are now calling the Moore's Law paradox. As we push process nodes deeper into the nanometer scale, chip complexity is just exploding. We're seeing things like a threefold spike in interconnect resistance, parasitic complexity that completely swamps traditional models, and advanced devices that can require up to 600 coupled equations just to simulate accurately. The old way, traditional CPU-based computation is failing to keep up.
And that computational gap is very, very real. It basically defines the entire verification and analysis crisis that we're facing today.
Exactly. So the solution that the industry is rapidly adopting is this fundamental shift toward what's called architectural alignment, using the graphics processing unit, the GPU. We're leveraging massive parallelism to break this bottleneck. So the central question we have to tackle today is this. Is the dramatic speedup we're seeing in certain EDA tasks, I'm talking about placement and design rule checking, is that proof that GPUs represent a universally transformative solution for the entire EDA flow? Or is this acceleration more of a specialized fix that's just masking some deep, persistent architectural limitations inherent to how GPUs process complex, sparse workloads? I'm going to argue that the GPU revolution is a necessary and, frankly, a proven path for solving these critical EDA bottlenecks.
And I'll come at it from a slightly different angle. I absolutely acknowledge those spectacular speedups. They are undeniable achievements. But I argue that the sheer scale of the engineering effort that was required to get them, it confirms my suspicion that these are highly specialized solutions. The GPU architecture, which is really built around rigidity and massive uniformity, imposes these severe structural restrictions, limitations in how it handles complex, non-uniform data, and that inherently restricts its widespread application across the entire design flow without constant fundamental re-engineering.
Okay, so let's look at why this architectural shift is even necessary in the first place. For decades, we tried to solve problems like placement using traditional CPU parallelism, and we hit a hard, measurable wall. For a critical task like global placement, throwing more CPU cores at it just gives you, quickly diminishing returns. You saturate the speed up at around 5x. The GPU architecture, on the other hand, it utilizes thousands of simpler concurrent cores. And this design is fundamentally aligned with problems like analytical placement, DRC, and large-scale simulation, precisely because those problems involve massive, repeatable computation.
That's a compelling argument for the hardware potential, sure, but let's talk about the software innovation that you need to unlock it. You cite DreamPlace, which achieved that transformative 35x speedup in global placement. That's huge. Taking a major design placement from half an hour down to less than a minute. But that wasn't achieved by just parallelizing some old C++ code.
Right, correct. It was achieved by recasting the analytical placement problem as a task that's equivalent to training a neural network, which allowed it to leverage these highly optimized modern deep learning toolkits like PyTorch.
And that is precisely my point about specialization. The huge gains, whether it's 35x in placement or that truly jaw-dropping 1257x speedup that XCheck got in design rule checking, they are engineered by completely redesigning the algorithms to avoid the core limitations of the GPU, not by just dropping in new hardware. The GPU's fundamental reliance on its single instruction multiple thread or SIMT execution model inherently clashes with the kind of complexity you find across most of the EDA flow, particularly in steps that involve extensive conditional logic and irregular data structures.
I see why you'd think that, focusing on the difficulty of the re-architecture. But what if the computational alignment just changes the cost-benefit equation entirely? Tasks like SPICE simulation and placement are inherently parallel at their computational core. The genius is leveraging these modern software ecosystems built for this kind of massive parallelism. We have powerful tools now like the Rapids QDF suite, which offers GPU-accelerated data frame manipulation and that speeds up pre-processing workloads by 10 to 100 times over traditional CPU pipelines. This is building a robust foundation for EDA work.
I appreciate the data on Rapids, But that's still focused on numerical calculation and data pipelines, which are by their nature very uniform. What happens when industry giants like Siemens or Cadence try to move something much more complex, say detailed routing or static timing analysis, which are inherently path-dependent and need frequent conditional checks?
Even then, the proof points are expanding. We're seeing industry adoption of GPU matrix solvers for SPICE simulation, and they're achieving reliable 8 to 10x speedups. This proves the shift is practical and scalable across domains, not just restricted to some theoretical placement study.
I'm just not convinced that scalability applies so generally, because you're focusing on the easily parallelizable numerical kernels while kind of ignoring the reality of control flow. The SIMT model is a rigid structure. For a GPU to work, thousands of threads in what's called a warp have to execute the same command at the same time. When those threads try to execute different branches of conditional code, a simple if-then-else statement based on local geometry, we get what's called branch divergence.
Which necessitates specialized kernel coding, I get that, but the benefits still outweigh the complexity in the end.
It doesn't just necessitate handling, it shatters the core advantage of parallelism. The GPU has to sequentially execute each of those divergent paths, which means any path not being executed forces those corresponding cores to just idle. Imagine a massive assembly line built to produce one specific part, perfectly. Then suddenly you throw in custom parts that all need different tools. That assembly line just grinds to a halt. Studies suggest this kind of inefficiency can account for about a 25% loss in performance on complex tasks. That's a huge structural impediment to general adoption across the flow.
I'll grant the control flow as a challenge, but if we can isolate and accelerate the most time-consuming computational kernels by 1 or even 2 orders of magnitude, then the surrounding overhead, even if it results in a 25% loss within the kernel itself, still yields revolutionary improvements to the overall design cycle. The key is finding these novel GPU-native algorithms. Let's shift focus to data structures, which is another area where innovation has been critical.
That's a good transition, because data structure efficiency is where these structural constraints become even clearer.
Exactly. Look at the success of XCheck, achieving that immense 1257x speedup in enclosing checks. What they did was convert complex DRC tasks into a massively parallel sweep line algorithm. This shows that even geometrically complex problems can be successfully mapped to a GPU. The focus is on restructuring the underlying data. For instance, in DreamPlace, they found that using pin-level parallelism was 1.9 times faster than the traditional net-by-net parallelism for wire length calculation. We're finding new, superior ways to organize and exploit parallelism that CPUs just couldn't touch.
I agree that sweep line algorithms work well for geometric checks, but you're highlighting uniformity again. Geometric checking deals with relatively uniform physical shapes. That is fundamentally different from the graph structures common in other EDA components, like netlists, which are highly sparse and full of pointers.
But can't we just reorganize that data structure to fit the memory model better?
Well, you can try, but the inherent irregularity fights against the hardware itself. GPUs are optimized for contiguous, uniform blocks of data. It's ideal for graphics, where pixels are right next to each other. When you introduce these irregular memory access patterns common to sparse structures, you create poor data locality. And the result is that the GPU's massive processor cache has become almost useless because the data it needs is scattered all over its high bandwidth memory. That memory is optimized for continuous, massive fetching. And when the data access is scattered, that core advantage just evaporates.
So the speedup is killed by the I/O bottleneck?
Yes, but it's more than that. When you try to parallelize heterogeneous elements, like massive clock nets right next to tiny noise mitigation nets, you inevitably end up with severely ill-balanced workloads among the threads. Some GPU cores finish their job instantly, while others are still slogging through these massive structures. This forces cores to idle, and that severely limits the speedup. The GPU architecture, which was designed for graphics rendering, is often fighting against the fundamental, irregular structure of the design data we work with.
You're focusing on the remaining hard problems and the architectural difficulty, And I think you're minimizing the importance of the kernels we've already solved. I maintain that the path forward is clear. Deep algorithmic innovation is the prerequisite for transformation. By achieving speedups of 35x in placement or 10x in simulation, the overall design iteration time is dramatically reduced. This is a game changer. This frees up engineering resources to go tackle the next challenges, like GPU-accelerated detailed placement and routability. The acceleration we've achieved in these critical kernels makes the re-architecture effort not just worthwhile, but economically necessary.
But that brings us to the most persistent challenge of all, the end-to-end flow. The very necessity of all this re-architecture just underscores how fragile the GPU solution is for a general integrated flow. The complete RTL to GDSI flow is not one single isolated kernel. It requires frequent interleaved steps and continuous interaction between the host CPU and the device GPU.
And that's where new interconnect technologies like NVLink or even newer, higher bandwidth versions of PCI, that's where they'll solve that problem.
That's a hardware evolution argument, but I disagree that the limitation is tangential. I think it is a fundamental architectural constraint of the accelerator model today. The key bottleneck is the latency you introduce by repeatedly moving gigabytes of design data back and forth across that interconnect. If an application lacks a high enough ratio of computation relative to memory transfer, and many complex or short burst tasks do, the latency from that overhead alone can cause the program to run slower on the GPU than on the CPU.
So that just dictates careful kernel selection. It doesn't mean the GPU isn't transformative for the right job.
It demands hypervigilance, which proves my point about specialization. Consider the XCheck example again. They use a dynamic algorithm selection strategy that chooses between a CPU and a GPU execution branch based purely on the layout complexity, specifically to avoid the GPU overhead on simpler tasks. If you have to engineer a complex decision layer into your software just to avoid running part of your tool slower on the GPU, that demonstrates how delicate and specialized the whole solution really is. It is not a drop-in universal solver.
I maintain that the need for massive parallelism to overcome the exponential growth of chip complexity is unavoidable. The successful implementation of deep algorithmic innovation, recasting problems into optimization frameworks, proves that we can unlock this hardware potential. The 35x speedup isn't an outlier, it's a blueprint. This is the only clear technological path forward for scaling to future node requirements, and it will inevitably lead us toward multi-GPU and distributed platforms.
And I conclude that while certain highly receptive computational kernels have seen staggering gains, these represent highly specialized solutions tailored specifically to fit the GPU's rigid SIMT paradigm. The inherent architectural limitations, branch divergence, the crippling inefficiency with sparse data, the persistent data transfer overhead, those remain significant structural challenges. For the broader EDA flow, this confirms that GPU adoption, while transformative in specific isolated areas, is fundamentally restricted to those problems that can be engineered into a uniform, massively parallel shape.
And so the tension remains, the incredible speedup we need versus the rigid architectural constraints we have to work within.
Indeed. It forces the entire industry to appreciate the intensive, dedicated hardware-software co-design required to truly harness modern computing for these classical EDA problems. There's clearly much more to explore here as this architectural alignment continues to evolve.